Welcome to Unite Now, where we bring unity to you, wherever you are.
Hello, and welcome to What's New in Unity's AR Foundation. Create augmented reality experiences that blend seamlessly into the real world. My name's Dan Miller, and I work as a senior developer advocate focusing on XR here at Unity.
I am Todd Stinson, a senior software engineer on the XR features team at Unity.
In today's session, we'll first start off by giving a brief overview of what is AR Foundation, talking about the different package versions and platforms, and then I'll briefly introduce how to get started with AR Foundation, installing the packages and configuring your scene for augmented reality. After that, Todd will go over some of the latest updates with the configuration management, giving you more control on how features are enabled within your augmented reality experiences. From there, we'll both overview some of the latest features enabled in AR Foundation, including meshing, depth, and the universal render pipeline. And finally, we'll talk about some projects made with AR Foundation. Let's go ahead and get started. AR Foundation overview. AR Foundation is available in the Package Manager and consists of different packages for the platforms like ARKit and ARCore, and the AR Foundation package, which is an abstraction that sits on top of these different platforms. Depending on the version of Unity that you're using, there's different verified versions of the packages. Here you can see in Unity 2019, the verified version is 2.1.0. The latest verified version is 4.0.2, verified in Unity 2020.2. This chart here shows the different package versions alongside the verified states with AR Foundation. The color blocking is indicating the different compatibilities that these packages have with the different versions of Unity. Looking at the bottom, we'll notice that the latest verified version of Unity, 4.0.2, is verified with Unity 2020.2, but it's still compatible and works with Unity 2019.4, the latest LTS version of the Unity editor. When thinking about the different versions of packages and whether you should be working in a preview state versus a verified state, we have some specific guidance around this. Verified packages have gone through the rigorous quality assurance testing required with certain versions of Unity. Preview packages have not gone through this quality assurance, but is where you'll find the most up-to-date features and functionality. The latest depth API is currently available in a previews package available with AR Foundation 4.1. When talking about what versions of Unity's AR Foundation works with what version of the editor, you'll notice that some packages, like Unity AR Foundation 4.0.2, are neither verified or in a preview state. This is because the package was verified with a newer version of Unity, in this case Unity 2020.2, but is still compatible with Unity 2019.4. A big idea behind Unity's AR Foundation is that you can build once and deploy anywhere. In this chart, we see the devices at the bottom. Next, we have the different native augmented reality SDKs built by the platforms. And on top of that, we have the platform packages, which are the integrations of these XR platforms into the Unity editor. AR Foundation sits on top of all these packages and gets data fed in through something called subsystems, which enable the different features and platforms within the augmented reality ecosystem. Here, depending on which build target you have, we'll link up the associated AR SDK behind the scenes. So if you're building for an iOS device, we'll link up ARKit, and if you're building for an Android device, we'll use ARCore. This allows you as a developer to just focus on building your augmented reality app, not worrying about platform-specific features like an ARKit plane or an ARCore plane, and instead just thinking about an AR plane. Let's get started with AR Foundation. First, we'll walk through downloading the packages. Next, configuring the platform-specific settings for mobile augmented reality. Then we'll set up XR management, modify an existing empty scene to use augmented reality, and finally, add some AR features like plane tracking and hit testing. I've loaded up an empty Unity project, and we'll start by going to Window Package Manager. This is where all the packages for AR Foundation live. I can filter the package manager by searching for AR. Here you can see the AR Foundation package, which we'll go ahead and install. Next, we'll install the AR Core package. Notice that there's a separate package for ARKit face tracking. Since our demo app is not going to utilize face tracking, instead we'll install the ARKit plugin. Now we've installed all the packages for AR Foundation. So let's configure the project settings under the Player tab in order to properly configure both the iOS and Android settings. For iOS, the first thing we need to add is the camera usage description, which will appear as a pop-up to our users the first time the application is launched. Next, we'll change the target minimum iOS version to 11.0. And finally, change the architecture from Universal to ARM64. Now, since we're building this project for both Android and iOS, we can select the Android settings here and configure them as well. The first thing is that we need to remove the Vulkan graphics API, since AR Core runs on OpenGL ES 3. From there, we'll want to make sure to configure the minimum API level. In this case, we'll use Android 7.0 or API level 24. Here in the XR settings, if we wanted to override some of the platform-specific settings, we could. Instead, we'll go to XR Management and make sure that the plugin providers for ARKit and AR Core are properly configured for Android and iOS. Now let's go and start configuring our scene to utilize augmented reality. To start, we'll delete the main camera, since we'll be creating an XR object that has a main camera or an AR camera already configured. This is the AR session origin. Next, we'll create the AR session. Now that we've adjusted the settings, added our functionality, we can go ahead and build out this project and see what each platform looks like. First, we get prompted in order to allow access to the camera, since we're using augmented reality. From there, there's no additional functionality. Instead, we just see a live camera feed from the camera on the device. Now let's add some additional functionality to our AR app. I'll start by adding an AR plane manager to my AR session origin. From there, I can go to my Create menu and create an AR default plane. Next, I'll drag it into the project hierarchy so that the default plane becomes a prefab. Then we can assign it to our AR plane manager component. Most managers in AR Foundation have additional settings. Here in the AR plane manager, we see that there's the ability to detect different planes for horizontal, vertical, or both. Next, let's create a C# script in order to place our object on planes. We won't use the start method, so I'll delete that now. We'll want to store serialized references for an AR raycast manager. And store a static list of AR raycast hits, which will be populated by our AR raycast. Next, we'll store a serialized field for our game object that will be instantiating on our planes. In Update, first we'll check to make sure that the touch count is greater than 0. Then we'll store a reference to the 0th index touch. Check the touch phase to make sure that we're only spawning a single object each touch. And next, we'll do an AR raycast from the AR raycast manager, passing in the touch position, populated with the hits list, and using the trackable type for plane within polygon, since we're raycasting on found planes. If we find a plane, we'll then store the pose from the 0th hit index, and use that for the position and rotation of the object we spawn. Back in Unity, we'll add the AR Raycast Manager to our AR Session origin, as well as adding our new script. Now let's create a simple sphere to place on our plane. First, we'll create a primitive sphere. We'll also create an empty game object, which will act as the parent for the object that we're placing. Since units in Unity are in meters, we want to scale down the sphere for AR. Next, we can offset our object so that the empty root object appears at the base of the 3D object. This will let the sphere be placed on top of the planes. If we don't set up this parent-child relationship, our sphere would penetrate through the plane and wouldn't quite look right. Lastly, let's turn this sphere object into a prefab and delete it from the scene, and then assign it to our script. Now let's build our project for both AR Core and AR Kit. Here you can see that both experiences act very similarly. We can find a plane, and every time I tap the screen, it places a sphere on the found plane.
Thanks, Dan. Now that we know how to get started, let's talk about some updates introduced in AR Foundation 4. For a while, we have actively listened to issues from developers where changes in AR Foundation settings did not result in expected change in device configuration. Configuration management, which had been implicit functionality in prior versions of AR Foundation, becomes an explicit operation that could be more openly handled. Breaking down the issue of configuration management, let's identify the source of the problem. AR Foundation supports multiple platforms. Each platform has a multitude of devices. Each device supports several configurations. Each configuration supports a different set of AR features, meaning that some features may not always be compatible with other features. Finally, for an AR session to run, one, and only one, configuration must be chosen. To solve this problem with AR Foundation 4, we added an overridable configuration chooser class. Let's look at 3 devices and setups. The Pixel 3, the iPad Pro with LiDAR, an iPhone XR, but with the ARKit face tracking package not included. This chart displays the number of configurations that are currently available on each of these devices. The Pixel 3 offers 3 configurations. The iPad Pro supports 6. The iPhone XR offers 5 because in this example, I removed the face tracking package. Thus, no configuration includes the user-facing camera. For clarity, we will focus on a specific use case targeting exclusively the iPad Pro with LiDAR. In this use case, we want to build an app that uses both the meshing functionality and the 3D body tracking functionality. Meshing is a supported configuration on this device. 3D body tracking is also supported in a configuration, but those are separate configurations. Because there is no single configuration that supports both meshing and 3D body tracking, these features may not operate at the same time. This is where the configuration chooser comes in. The job of the configuration chooser is to look at the available configurations that are possible and to choose a configuration that best matches the needs of the application. Let's dive into a specific example by looking at the code for the default configuration chooser and writing our own. This is the code for the default configuration chooser. This implementation is extremely simplistic. The goal of the default configuration chooser is to choose the configuration that matches the most number of features. That's it. Nothing fancy, simply choosing the configuration with the maximum number of matching features. Dissecting this code, line 9 illustrates that all configuration choosers derive from the abstract class configuration chooser. This abstract class has one abstract method that you must implement, the choose configuration method on line 27. This method is given 2 parameters. First, the set of all available configuration descriptors, and second, a set of requested features. The requested features include all features being requested across all active AR subsystems. The choose configuration method is expected to return a single configuration. This method starts with a few sanity checks, ensuring that valid descriptors are passed in, ensuring that at least one tracking mode and at least one camera mode are requested. The core of this implementation iterates over each of the available configurations to find the configuration with the highest capabilities matching the requested feature set. If there are multiple configurations that have equal number of matching feature counts, the tie is decided by a rank value. Each configuration has a rank value that is set by the device provider. This value is only used in the instance of a tie to serve as a tiebreaker. After each available configuration is checked, The configuration with the highest number of matching features is returned and becomes the configuration for the active AR session. This simple logic should suffice for most AR applications. However, we can override this behavior with our own configuration chooser. Let's focus on the scenario where we want our app to switch between the front-facing and rear-facing cameras. And we want our camera choice to take precedence over all other AR features. We can now achieve that behavior with our own configuration chooser. This sample does just that. We are putting this code into a monitoring behavior so we can attach it to a game object. We have a field for the AR session that we will be modifying. In the start method, we create a new instance of our configuration chooser and set that to the AR session subsystem as shown on line 26. Next, we have our own configuration chooser implementation. As before, we derived from the configuration chooser abstract class and implemented our own choose configuration method. We still do the same sanity checks as before. On line 55, we see new code for implementation. With this line, we are extracting only the camera features from the set of requested features. We are explicitly remembering which camera feature is requested. On line 63, like the previous code, we walk through each of the available descriptors and count the number of features that match the requested feature set. The main difference in our implementation are lines 66 through 68. This code adds extra weight if the configuration matches our requested camera features. This basic heuristic gives configurations with the matching camera direction an added bonus to ensure that it's preferred over all other AR configurations. The rest of the code is almost identical to the default implementation. We still choose a single configuration with the best weight. However, we have given configurations with the matching camera directions an added advantage so that they will be preferred. Let's see how this runs. This is our test scene. We have a game object that will display the AR session information to the device screen. And we have added a configuration chooser game object. On the configuration chooser game object, we have a basic script that will toggle the requested camera direction when pressed. And we have our own configuration chooser component that will override the default chooser. First, let's build with our configuration chooser disabled. Be sure to build a development build, as there are additional login information about the configurations in a development build. The build is deployed to my iPad, and we can see that clicking the swap camera button does have an effect. The session information reports that the requested facing direction is changing from world to user, but the current facing direction never changes. This is expected behavior with the currently active subsystems and using the default configuration chooser. I will point out some additional information about the configuration that is logged only in development builds. When a configuration change occurs, you'll see some debug information logged. This information includes the complete set of requested features, the features that are supported in the chosen configuration, and the features that are not satisfied by the chosen configuration. As you can see in this run, the user-facing camera is not satisfied by the chosen configuration. For iOS, this log information will appear in Xcode. For Android, this log information may be found in the logcat output. Let's go back to Unity. Let's enable our configuration chooser script, and let's build again. The new build is deployed to my iPad. We can see that clicking the swap camera button has our desired effect now. The camera facing direction has changed, but do note the other subsystems that had been running are no longer running with this configuration. This is because these features are not supported in the new configuration. Refocusing on the log output, we can see the configuration debug information calls out which requested features are not satisfied in this configuration. In summary, writing your own configuration chooser will give you more power to control your AR application state.
Thanks a lot, Todd. Now let's talk about AR Foundation's latest features. Meshing, which is enabled on the latest iOS device with a LiDAR sensor, generating a runtime mesh that can be used for occlusion, collision, and more. Depth, which is an API that returns a unique depth image at runtime. This can also be used for occlusion, as well as applying unique effects to the world. And finally, Universal Render Pipeline. Now that Universal Render Pipeline has been officially released out of the preview state, the support within AR Foundation is much more robust. This enables things like shader graph, VFX graph, and more. First, let's talk about meshing. This was enabled in ARKit 3.5 and greater, and requires AR Foundation 4.0 and greater. It's available on iOS devices with a LiDAR sensor. It is not currently available on Android or AR Core. Within the Mesh API, there's a set of unique classifications for different surfaces. These include ceiling, door, floor, none, seat, table, wall, and window. When enabling meshing within AR Foundation and ARKit, if you also enable plane tracking, it smooths out the meshes for horizontal and vertical surfaces where planes would be found. If you want a more accurate mesh, it's recommended to not enable plane tracking, as it'll pick up on the finer details and not try to flatten surfaces. Here's a demo built on top of the latest AR Foundation and ARKit meshing. You'll see that there's a reticle that snaps to the currently found mesh. Depending on the surface I'm on, which is labeled in the top part of the screen, different icons will appear for me to place content. Here I'm looking at the floor, which allows me to place this dresser and the chair. And now when I'm looking at the wall, I have the option to place a clock as well as 2 different picture frames. The way this demo works is it's looking at the mesh classification and providing the user with different UI buttons depending on what surface they're looking at. Here I have the ability to go in and visualize the mesh. You can see that the different surfaces are colored. For the wall, we have purple, for none, we have green, and for the floor, we have yellow. You can also see the mesh being generated there at runtime. Now let's walk through how this demo was created and where you can get access to it. Here in Unity, we have a Mesh Manager. It has the AR Mesh Manager component on it, which is required to be a child object of the AR Session origin. Like other managers within AR Foundation, there's some additional settings associated. For ARKit meshing, the only settings that are applicable are the normals and the concurrent queue size, as well as the mesh prefab. As ARKit is constructing mesh geometry, the vertex normals for the mesh are calculated. You can disable the normals if you do not require the mesh vertex normals to save on memory and CPU time. To avoid blocking the main thread, the task of converting the ARKit mesh into a Unity mesh and creating the physics collision mesh, if there's a mesh collider on the mesh prefab object, are moved to a job queue processed on a background thread. Concurrent queue sizes specify the number of meshes to be processed concurrently. Now let's take a look at our mesh prefab. Depending on which components are on the mesh prefab, will determine how your mesh is visualized and how it interacts with the real world. Our prefab requires a mesh filter in order to work properly. Here we also have a mesh collider, so our prefab is generating collision geometry. If we were to also add a mesh renderer and assign a material, then we could visualize this base mesh. Since we're just using this for physics collision, we only require the mesh filter and the mesh collider. The key components of this demo are classifying each mesh and the surface through the classification API, which determines which classification of the mesh the reticle is raycasting to. From there, we're also showing the reticle and snapping it to the generated mesh, and finally, placing objects aligned with the mesh based on UI. For classifying each mesh, I'm using a slightly modified version of the mesh fracking script available in AR Foundation samples repository. This creates unique meshes that update at runtime based on each classification and the return vertices. By default, this script enables the meshes and has a visualization on them. I've set the transparency of each mesh visualization or each mesh material to be completely transparent, so they're not visible by default. For raycasting against these meshes, I store a dictionary, and that is storing both the trackable IDs as the key for each unique mesh and a native array of the mesh classifications. From there, I subscribe to the mesh changed event from the AR manager and manage the mesh dictionary based on a list of mesh filters returned from the AR mesh changed event arguments. From there, I'm adding, updating, or removing items from the dictionary. And one small note here is that we're using and capturing the trackable IDs from the mesh name. Now that my dictionary is properly managed, the next step is to use a physics raycast in the update method based on the center screen position. My base mesh here has a mesh collider on it. And by default, the way the meshing system works is that it updates this mesh collider on a worker thread every frame if the base prefab has the mesh collider on it. With my physics raycast, based on the hit result, I'm again extracting the trackable ID from the name and storing the triangle index from the physics hit in order to search through my dictionary and return the correct classification based on which triangle of the mesh I'm hitting. Here we're doing some safety checks to make sure that our trackable ID is contained within the dictionary, as well as the triangle index within the range. From there, I am storing the classification in the current classification field by using the mesh ID as the key to my dictionary and the triangle index as the index in my stored native array. Lastly, for displaying the name, I'm simply converting the enum value to a more readable string that I set in the UI. For the reticle, we have an optional boolean for snapping the reticle to a mesh or found planes. Since I want the reticle to appear on all the unique surfaces, I'm using the snap to trackable type plane estimated, as this is what ARKit is expecting when doing an AR raycast against the mesh. Finally, in order for the reticle to maintain a visible and constant size, I'm scaling the size of it based on the distance away from the user, or in this case, the camera transform. For placing, I'm linking into the classification manager and checking for table, floor, and wall surfaces. Based on those surfaces, I'm displaying some unique UI and linking into a list of prefabs in order to instantiate different objects based on the reticle position. I'm also doing a little bit extra to rotate some of the floor and table objects so that they always face the user when they're instantiated. And now I'll hand it over to Todd to talk about depth.
Depth textures are a new feature added recently to both AR Core and ARKit. AR Foundation 4.1 Preview introduces support for environment depth textures and automatic occlusion. With environment depth enabled, the device produces a texture per frame representing the distance from the camera to the visible real-world surfaces. The range and accuracy of depth information varies across devices. Some devices use a time-of-flight sensor, whereas other devices might use alternate techniques to estimate the depth. Depth images from AR Foundation are a single-channel texture in either a R16 or a R32 format. Each pixel in the single-channel texture is a floating point value that represents a distance in meters. Depth textures are commonly used to render occlusion between virtual content and real-world geometry, thus deepening the visual integration of the experience. Additionally, you can use depth images with computer vision algorithms to build scanning apps that construct virtual content based on real-world geometry. Both AR Core and ARKit now support depth textures. AR Core 1.18 introduces support for depth on a subset of Android devices. For iOS, ARKit 4 adds depth support on devices with the LiDAR sensor, like the new iPad Pro. With depth information, AR Foundation offers automatic occlusion functionality. When enabled on supported devices, depth information is written into the Z buffer during camera rendering background passes. With this depth information in the renderer, virtual content that is farther away will be occluded by nearby real-world surfaces. Likewise, when virtual content is closer to the camera, this content will occlude the real-world camera background, thus giving the appearance that virtual content is interacting in the real world. To set up, you just add the AR Occlusion Manager to your AR camera game object and enable the environment depth mode. For environment depth, there are 4 possible settings: disabled, fastest, best, and medium. Disabled will disable the environment depth texture entirely. The other 3 settings offer a range of rendering qualities, but with the trade-off that each more advanced rendering choice comes with additional frame computation. You will need to tune your rendering quality to achieve the desired results for your app without incurring excessive computational overhead. Let's look at a demo of automatic occlusion in action. With automatic occlusion enabled, we can see this flying robot will get occluded by passing vehicles. The depth texture, updated per frame, provides a depth value for each pixel against which the robot is clipped when it is behind. Also, we can move the camera behind this post to show how the post will occlude this virtual content. The depth texture can be used in numerous ways. Let's walk through an example of accessing that depth texture inside a shader and displaying a picture-in-picture view of the depth information on top of the camera background. We start with a depth gradient shader. Because the pixel values are in meters, we need to convert that information into colors to better visualize the data. We are going to pass the depth texture into the shader through the main text property. Because the pixel values are in meters, we need a range of distances over which we're going to visualize this data. Thus, we have min and max distance properties. The depth image remains in a fixed orientation, regardless of how the user holds the device. To compensate for that device orientation, we need to rotate the texture for a good picture-in-picture view. The vertex shader sets the position and texture coordinates for each vertex. Using the texture rotation property, we do an affine rotation of the texture coordinates. This is standard color conversion from the HSV color space to the RGB color space. Moving into the fragment shader, we first sample the depth texture, but we only need the red component because the depth texture is a single channel. This gives us a distance in meters. Next, we do some linear interpolation math to map our distance value from a value between min and max distances to an HSV color. By interpolating the hue component as such, we were mapping nearby distances to be blue, medium distances to be greenish turning to a yellow, and faraway colors to be red turning to a purple. Finally, we convert our HSV color to an RGB and return that as the fragment value. Next, let's look at our component script. We declare the names of the shader properties that we want to use, and we look up the property IDs to make setting the values to the material quicker. We have some internal fields that we store temporary state information. We have some fields that show up on the game object and will be serialized with a scene. Getting into the real code, we start in the onEnable method, where we store the initial screen orientation and we update the raw image UI element. We will get into the update raw image method shortly. In the update method, we make sure that the device supports the environment depth image. If it doesn't, we display a message on the screen and early exit the update method. We grab the environment depth texture off the occlusion manager. Then we log some information about the texture, either to the screen or to the debug log. We set the environment depth texture to the raw image. We compute the aspect ratio of the environment depth texture. The aspect ratio can change, most commonly when the camera configuration changes. The environment depth texture aspect ratio typically mirrors the screen aspect ratio from the camera configuration. Finally, in the update method, if either the screen orientation has changed or the texture aspect ratio has changed, we want to update the raw image UI to best reflect these changes. When we log texture information above, this is the information that we log: the texture format, the texture dimensions, and the MIP map account. In the update raw image method, we want to configure the raw image UI and the environment depth texture rendering to match the screen orientation and the texture aspect ratio. This will provide us with the most optimal picture-in-picture view. Lastly, we update the raw image UI element with the new dimensions and material properties. Switching to the Unity scene, first, let's note that in this demo, we've added the AR occlusion manager to the AR session origin rather than to the AR camera. For this demo, we want to use the depth textures not to do automatic occlusion, but to use in our own custom shader. Automatic occlusion is enabled if we add the occlusion manager to the AR camera with the AR camera background component. However, in this specific case, that is not the behavior that we desire. We do not want to enable automatic occlusion. We achieve this by adding the AR occlusion manager to any other game object. In this example, we've added it to the AR session origin. Next, we put our script component on an otherwise empty game object. And we have hooked up the required fields for the occlusion manager, the raw image UI, the texture image info, the depth material, and the maximum distance value. Let's build this scene to see how it works. As you can see, we have a picture-in-picture view of the depth image overlaid on top of the AR camera background. We can see that the depth image updates in real time. Let's move on to another example of how to use depth texture in a scene. Fog effects can be used to add ambience to your experience. What if you could add fog using the depth measured by the device? To start, we begin with a shader. We'll start with a background shader, the ARKit background shader in this example. And we remove the parts that we don't need for our demo. For the properties, our shader needs 3 textures. The first 2 textures are how ARKit provides the camera video for the background image. This is a standard YCBCR color space. Next, we have our environment depth texture. In the vertex shader, we are transforming the geometry, which will be a full screen quad, and remapping the texture coordinates based on the device orientation. In the fragment shader, we read the ARKit camera video textures and transform the color from YCBCR color space into the sRGB color space. If the project is using linear color space and not the gamma color space, we need to convert our sRGB color space to linear. We read the red channel value from the single channel environment depth texture to get a distance value in meters. And we convert that distance value into a depth value for the Z buffer. With the Unity fog functions, we use the depth value to calculate a fog factor, which is then used to linearly interpolate between the background color and the scene's fog color. Finally, we return the computed color and depth value for the fragment. Switching over to our Unity scene, first we'll start with the light settings. Under Window, Rendering. In the Other Settings section, we enable fog. We have the fog mode set to linear, with the start distance at 0 and the end distance at 35. On the AR camera, we have added an AR occlusion manager with the environment depth mode set to best. In the AR camera background component, we have enabled used custom material, and we have added a material that uses our custom fog background shader. Finally, we have a simple script component that will change the fog end distance based on a UI slider so that we can interactively manipulate the fog at runtime. That's it for our changes. Let's build and run. We have a robot standing at the end of the hallway. We alter the fog distance using our slider. We can see as the camera moves, the fog calculations are using the depth values from the device to shade the background. Looking at both the meshing and the depth functionalities, you might notice that you can achieve occlusion effects by using both approaches. So you might be wondering, is one approach better than another to achieve an occlusion effect? Mesh-based occlusion will give you nice smooth boundaries on surfaces. You will see less jaggies along edges, and for some cases, meshing will give you a better visual appearance. However, meshing has its downsides. Most notably, while it will work best in static environments, it will fail miserably in highly dynamic environments. This is because it will take several frames after the surface is scanned before the mesh geometry is updated. Additionally, there are computational costs with computing mesh. This results in more power consumption and more heat for the devices. Depth-based occlusion works well in dynamic environments. The depth texture is updated on a per-frame basis. The demo with the flying robot on the street earlier, with the vehicles passing by, was using depth-based occlusion. That demo would be impossible using mesh-based occlusion. Moreover, depth is supported on both Android and iOS platforms on a subset of devices.
Thanks, Todd. Now let's look at universal render pipeline support, which was added in AR Foundation 3.1 and above. It's enabled through a pipeline asset custom render feature and becomes enabled once you've added AR Foundation to a project with Universal Render Pipeline. Universal Render Pipeline supports shader graph on all the supported platforms, as well as VFX graph on specific platforms depending on the enabled graphics API. Here we are in the Unity project that we used for getting started. Let's go ahead and open up the package manager and install the Universal Render Pipeline. After we've installed the package, we can go to the Create menu and select Rendering, Universal Render Pipeline, Pipeline Asset. This creates two objects in our project. In the forward renderer, we can go and add the additional render feature with the button at the bottom. Once we've done this, we can go into the graphics settings and assign our universal render pipeline asset. Notice that the sphere in our scene turns pink. This is because it was utilized built-in renderer. By assigning the universal render pipeline in the graphics setting, we've overridden the renderer. Luckily, Universal Render Pipeline has a built-in method to update all of your standard materials that you already have in your project. This swaps known legacy shaders to the equivalent of Universal Render Pipeline shaders. It does not convert any custom legacy shaders that you might have in your project. You can find this in the Edit, Render Pipeline, Universal Render Pipeline, and then you have the option to upgrade selected materials or all materials in your project. Notice once we do that, our material is rendering properly and we can build out to our devices. Now let's take a look at the opposite. Here we have a Universal Render Pipeline project, and let's add AR functionality to it. We'll start by opening up the Package Manager and downloading AR Foundation. Here I'm grabbing AR Foundation 4.0.2. Now that AR Foundation is enabled, the next step is to locate the render pipeline asset and add that rendering feature, similar to what we did in the previous project. With the Universal Render Pipeline enabled, we can do cool visual effects without coding specific shaders. We can also enable the VFX graph, which is the next level of particle simulation, enabling complex simulations and visualizations. I want to wrap up this presentation by talking about some sample repositories that are available for you when getting started and working with AR Foundation. The first repository is AR Foundation Samples. This is available on the Unity-Technologies GitHub with AR Foundation-Samples. This project covers all the features enabled in AR Foundation, unique scenes and examples for each of the features. It also has a loader scene, so you can try out all the different features and scenes in a single built application. This is helpful for understanding what features are supported on your AR-enabled device, as well as just trying out and understanding the examples more. Next is AR Foundation Demos, also available on the Unity-Technologies GitHub repository under AR Foundation-Demos. These are fewer projects that are more focused on single features as well as higher quality polish. This includes a UI/UX framework for guiding your users, and recently we added localization support. There's also an example of how to do image tracking by properly referencing the GUIDs, as well as being able to attach unique objects to unique images. This demos repository contains many of the demos that you saw here, including the meshing placement example, as well as the fog demo. Documentation is included in the README, as well as some of the projects being hosted on the Unity Asset Store. And last but not least is Unity Mars. This is a project specifically built on top of AR Foundation. So all of the unique and new features that we talked about today are enabled within Mars. It is a set of specific tools and functionality specifically designed for building augmented reality within the Unity editor. This includes the ability to test and simulate what augmented reality experiences are like in different simulated environments, as well as things like fuzzy authoring that enables you to procedurally place content around the world. Find out more at unity.com/product/UnityMars. Thank you very much for coming to our presentation. I hope you learned a lot about AR Foundation, some of the latest features, and more. If you have additional questions, you can meet us on the forums for a Q&A specific to this session.